Hello. In the last section, we talked about solving a system of equations just by graphing the two lines. And I think we mentioned that's probably not the best way to go about it, because if you draw the line a little crooked or it doesn't quite have the right slope because of, human error, it's not going to work out very well. So this section gives us two different methods on how to solve a system of equations algebraically. And these methods are a lot more foolproof. The only way these could go wrong is if you make some kind of algebraic error or arithmetic error, that kind of thing. So in this section, I would still probably check my answer just like we did in the previous section. It's just that you probably don't have to worry as much about doing something wrong in this section. Okay, so as the title says, we're solving by the first method we'll learn is substitution, which I think that's probably the easiest method to pick up on right away. The second method we'll learn is elimination. That one, it takes a little getting used to. It's kind of strange. But once you get the hang of both of them, actually I've noticed most people prefer the second method. And I would agree. I think I like it better. It's more clever and, I don't know, easier. But it does take some practice to master. So that's the only problem. But okay, let's see. We'll look at the first method here. So we have an example. They want us to use the substitution method, and we're given a system of equations here, like the ones we saw in the previous section. You got x plus y equals 7, and then the other one is y equals x plus 1. So notice in this one that the second equation has y isolated, which is significant for this method. We're going to need to have one of our equations have a variable isolated. So either x could be by itself or y could be by itself. Okay, so we have this system of equations, and as it says here, notice that the second equation, y equals x plus 1, the one we pointed out has y by itself. It tells us that y is equal to x plus 1. So in my mind, kind of the way I think of it is, if y is equal to x plus 1, I should be able to replace y anywhere I see a y with x plus 1, since they're equal. So anywhere I saw a y, even the y in the first equation, I should be able to replace it with x plus 1 if I wanted to, because the second equation tells me that they're equal. So let's see, I'm going to, just like it says, and just like we kind of talked about just now, we should be able to replace y in the other equation with x plus 1, since y and x plus 1 are equal to each other. So the top equation that we haven't really looked at yet was x plus y equals 7. But from the other equation, we know that y is equal to x plus 1. So I should be able to take y in the equation x plus y equals 7 and replace it with x plus 1. So that's what we've done in this next step. The wording that we use is substitute. So we've substituted x plus 1 for y. Where y used to be, we put an x plus 1. But notice that the equation stays the same otherwise. You got the x in the front, the 7 on the other side of the equal sign. The only thing that's changed is you've replaced y with x plus 1. And that's okay because the other equation told us they're equal. And then the most important thing about that is notice now that equation has only one variable left. It's got an x, well, it's got two x's, but it's possible to solve an equation that has more than one of the same variable. It's just impossible to solve an equation that has two different variables. We've really got it down to a really nice thing now. We've got x plus 1 equals 7. And I put the parentheses there just because whenever you substitute something into an equation, it's a good idea just because there are some times where you won't know what to do. What's the operation between that and something else that was already there? So yeah, it's a good idea to keep what you're substituting in parentheses, but at this stage, the highlighted stage here, I realize I don't really need the parentheses, so I'm just going to keep in mind that this x and this x are like terms. So they can be combined. X plus x makes 2x, and then I'll just carry this 1 down since it has no like terms. And then I'll just start solving for x. So first thing I'll do is, like I said here, solve for x by subtracting 1 from both sides. That's what we've done. Once you subtract 1 from both sides, 2x is all by himself. And then on the right side, you have 7 minus 1, which is 6. then we almost have it solved. I just have to divide both sides by 2, and that'll get x by itself. So x will be equal to 3. So that's the idea behind substitution, is try to have one of your equations have a variable isolated, like we have. The second equation had y by itself. Then you're going to substitute for that variable in the other equation. It takes some getting used to. But another thing is, remember from the last section that the solutions to these systems should be ordered pairs, because what you're looking for is where do those lines intersect, really. So my answer should be an ordered pair. And so far I have found the x value, 3, to this system of equations, but I have not found the y value. So even though we've solved it, we've only solved for one variable. But now, like as I wrote here, what's the value of y? Well, we can find y by substituting x equals 3 into either of the original equations. I think the second one's usually easier. The one, or whichever one has a variable isolated, that's usually the one that's going to work out nicely. Although you could substitute x equals 3 into this equation, or the other one actually, the top one. You'll get the same solution either way. But I think if you had to choose, this one's a lot nicer. Alright, so since x is equal to 3, we just found that out earlier. I'm going to substitute that guy in here for x. And then y just kind of falls into our lap. Y is equal to x plus 1. But since x is 3, it's 3 plus 1, or 4. Alright, we found the ordered pair. We found that x was 3 and y is 4. And you can always check it like we did in previous sections, where you take that ordered pair, 3, 4, you replace the x and the y in both of the equations you were given with 3 and 4, respectively. Make sure that they're both true statements. Maybe we should do that, huh? Let's see, maybe at the top here. So the first equation was x plus y equals 7. And I think from this ordered pair that x is equal to 3 and y is equal to 4, because those are the solutions, or the components of the ordered pair. And when I substitute them in the first equation, I do get that it's a correct answer. 7 is equal to 7. But like we've seen before, it's not enough to test it in just one of the equations. You have to test it in both. So I'm also going to test it in the second equation, y equals x plus 1. In my ordered pair, y is equal to 4 and x is equal to 3. I'm going to go ahead and replace those guys and see if this ends up being a true statement as well. 4 equals 3 plus 1. Yeah, that's true, right? 4 equals 4. Okay, so we've tested both the ordered pair in both equations, and we found that it holds true for both. That means that this guy is the solution. 3, 4. It's a lot more exact than if I were to graph both lines. That's probably not the best way to go on these, because it's not very exact. So that's the idea behind substitution. We'll try a few more, and I think we'll get the hang of it. It's kind of hard to get used to, but that's the idea. So notice in this next example here, part A here, we have two equations where neither variable is isolated. So in the last example, we had y by itself in one of the equations. So we need to make that happen again here. And you don't always have to solve for y. I would say try to isolate whichever variable looks the easiest to isolate. It could be an x or a y, and it could be the first or the bottom equation. It doesn't matter. Isolate either variable in either equation. It doesn't matter. It's totally up to you. Equation. Yeah. So I would look at all these variables. You have a 3x in the top equation. You have a negative 4y in the top equation. You have a 5x in the bottom equation. And then you know what the nice thing is, in the bottom one you have just a nice little y with nothing in front of it, no coefficient. So I think just for that fact, y has no coefficient. I mean, it has a coefficient of 1. Y has a coefficient of 1. That makes it a lot easier to solve for. So I think I will solve for y. This whole process would work if you solve for x or y in the other equation. I mean, you could choose any of them and it'll work. It's just you want to make it easiest on yourself. So if one of the variables in either equation looks easier to solve for, I would definitely try that. Alright, so I'm going to grab the second equation. I've decided to isolate y because it seems easiest. And I think it is, because all I have to do is move this 5x over. So y is equal to, and at this point you have the freedom, you could write this as 8 minus 5x or negative 5x plus 8. I think before we always wrote the 5x first, negative 5x plus 8. But that was only because we were trying to graph the line. And we wanted it to look like mx plus b. But in this type of problem, we don't really need, we don't really need it to look like that. So you can write it either way and it's not really going to hurt you. Alright, so at this point, we're kind of where we were in the last problem. We have y by itself on one equation. What we're going to want to do is substitute that in the other equation for y. Substitute for y in, and then I look back at the original system and I say, okay, which of those two equations have I not looked at yet? The top one is the one I haven't looked at yet. So I'm going to rewrite him, but I'm going to replace his y with the thing that I have in the circle here. Since, again, the first equation tells me that y is equal to 8 minus 5x, so I should be able to replace it here. So where this y was in the second equation, I've went ahead and replaced it. And then you're doing well if at this point you only have one variable left. So notice in this equation that we just wrote, there's only an x, there is no y. Although there are two x's still, that's a good sign, that means you're doing the right thing. So I think this one's going to be a little more complicated to simplify. I'm going to have to distribute this negative 4 into the parentheses. So if I multiply that, negative 4 times 8 will give me negative 32. And then I got to be careful here because I have a negative 4 times negative 5x. That's positive 20x. And then equal to the same number that was already on the right side, 14. And then I look at what I have a couple like terms, 3x and 20x. I'm going to combine them to make 23x. And then we have the 32 that's also on the left side, equal to 14. And now that I've substituted the y, y equals 8 minus 5x in for y, and simplified as much as I can, now it's time to start solving for x. So I'm going to try to isolate x by moving the 32 over first. And 23x is equal to 14 and 32 is 46. Alright, and now if I isolate x completely, I'll divide by 23 on both sides. And that'll give me 2. I believe 23 goes into 46 twice exactly. That's a good sign. If you get kind of your answers could be fractions. Like say this fraction didn't reduce. That's fine, but I'd say about 80% of the time you're going to get whole number answers or negative whole number answers. So we found x, but just like in the last problem, we got to keep in mind that you want to know what x and what y are. You have to know both to have a complete solution. So it's a good idea to start setting up your ordered pair right when you find one of the variables to remind yourself that you have to find two numbers. So now to solve for y, I'm actually free to substitute x equals 2 into any equation, one of the original two that I had that they gave me right off the bat. Or actually, I think the easiest one, like we said in the last problem, the easiest equation to substitute into is the equation where one variable is by itself. That's going to be the nicest one. But you do have the freedom, you could substitute the value we just found, x equals 2, into the first original equation they gave us, or the original second equation, and you would get the same answer no matter what. So don't worry, no matter where you put the value you just found, you're going to get the right answer for the other one. Just, you want to make it easier on yourself if you can. Okay, so let's substitute, because x equals 2 is what we found. And let's simplify that. Y equals, okay, that's 8 minus 10. And if you combine those like terms, you get negative 2. There we go. So we found x and we found y. That must be our ordered pair. Beautiful. And you could check it again like in the last one. Remember we said your x value is positive 2 here. Your y value is negative 2. You'd have to substitute those into the top equation that you were given initially and see if it's true. And then substitute those in the second equation you were given initially and see if that's true. So you'd have to do both. That's the main thing to keep in mind. Alright, hopefully it's making more sense the more of these we do. Let's try this next one. These ones always throw me off because it's not x and y, right? It's a little confusing. But still, what I would say is look at these equations, both of them, and say, which variable does it look like it's the easiest to solve for? And I know in the last example we just did, we said, oh, y was easiest to solve for because it had a coefficient of 1. So that was what made it easy to solve for. In this problem, I think we kind of have a choice. I noticed this m in the first equation has no, a coefficient of 1, so it'll be easy to solve for. But also the n in the second equation is kind of nice. It has no coefficient. So I think this one is a toss-up. I don't know if it's better to solve for m in the first one or n in the second one. It's totally up to you, and I don't think there's a better, which one's better or anything. But for some reason the top one's calling to me, so I'm going to solve the top one, m minus 2n equals 16 for m. And then I'll try to substitute later, but first things first, I'm going to try to solve this for m. But that's not too bad. All I have to do is move the 2n over. So m's by itself now. And you have the freedom to write the right side as 16 plus 2n or 2n plus 16. Doesn't really matter, it's just personal preference, so you could write those terms in any order. Okay, now that we have one of the variables isolated, I'm going to say, okay, which equation have I not used yet? I'm going to substitute into the other equation. So that I use the top one to solve for m. Now I'm going to focus on the bottom one. 4m plus n equals 1. But now that I know what m is equal to in terms of n from the previous equation, I'm going to take that and replace it where m is in the second equation. Again, because m is equal to 2n plus 16, I should be able to replace m with that quantity. Let's see what happens. The 4 is still there. And this is an example of where it's a good idea to put parentheses, because if I don't put parentheses, I wouldn't know what's going on between the 4 that's in the front and this 2n plus 16 that I'm just writing. So it's always a good idea to put parentheses just so you know what to do. Okay, now it's a good sign that the equation we're ending with right now has only one variable. There's an n but no m. So I can solve this, but I'd have to distribute that 4n first. So I'll do 4 times 2n, that's 8n. 4 times 16 is 64. Okay, then you have n that was already there in that equation. So that looks good, and we have a couple like terms now. 8n and n make 9n plus 64 equals 1. And now we're ready to start solving for n. The first thing I would do is subtract 64. And then we'll be left with 9n equals negative 63. And the last step to get n by itself would be divide both sides by 9. Let's see, and I believe, what's 9 and negative 63? Negative 7. Looks good. So we have n, but again, you should have two values, one for each variable in the end. And this one, I think we've talked about this before. We just found n, but I say, okay, if this was x and y, I would know which coordinate the negative 7 goes in. But remember, if it's not x and y, just think, okay, what are my variables? Whichever one comes first in the alphabet should be on the left, so m. And then the one that comes second in the alphabet should be on the right, so n should be on the right. And since I just found n is negative 7, that'll be the right component of the ordered pair. But now if I want to find the left component, like we did in the last one, I'm free to take this value of n equals negative 7, and I can replace it into either of the original equations. Or the better way is to take that equation that you found once you isolated m. So I had m equals 2n plus 16. That's the nicest one to substitute into. But again, I think, like we said before, it would work if you substitute n equals negative 7 into any, either of the original equations as well. That would be fine. But anyway, I like to make it easier on myself if I can. So I'm going to go ahead and replace n in that equation. So negative 7 is going where n was. And now we've got m equals, okay, 2 times negative 7 is negative 14. And you're adding 16 to that. That means you're going to get 2 for your value of m. And now we're all done. There's our ordered pair, 2 comma negative 7. And I'd say for sure if this was on an exam or something, I would check that solution in both equations just to be safe. Because you want to do all that work and somewhere along the way you made some little mistake, like you forgot a negative or something. You'd rather check your answer and make sure you got it right. If you got it wrong, I'm sure it's some algebraic error, you missed a negative or you added wrong, some little thing you'd have to check. So, I mean, we did a few examples of that, but I've kind of outlined the steps here in this box, just in case later on you come back and you're trying to review how to do this and you say, man, I completely forgot how to do that substitution method. And then you have steps kind of on how to do it. So maybe we'll just talk about them real quick just to reiterate. The first step was you want to isolate a variable in one of the equations, unless one is already isolated. Because remember, in the first equation that we looked, or the first problem we looked at, one of the equations already had y by itself. So this first step is not always necessary, but if one of the equations, or both of the equations, do not have a variable by itself, then you will have to get one by itself. And you have the freedom to choose any variable you want. It's up to you, whichever one looks easiest. And then once you have that, step 2 is you want to substitute for that variable in the other equation using parentheses. So you're going to rewrite the other equation that you haven't looked at yet and substitute into that equation with the other equation that you've isolated a variable with. Let's see, then once you do that, the next step was, at this point you should only have one variable, like we kind of pointed out a few times. So you should be able to solve the equation, and you'll find the value of either x or y, or if you have different variables like m and n, you'll find one or the other. And once you have one, then you're almost home free. You can substitute that into either of the equations, the original equations, or like I pointed out here, I'd substitute it into the equation that we got from step 1, which is the equation that has a variable isolated. That's usually, or it's always the nicest one to substitute into. And at that point, you should have the value of both equations, or sorry, both variables. So you should be able to write it as an ordered pair, x comma y, or m comma n, whichever letters you have. Okay. So I think that was pretty good. We did a few examples, but I want to save most of our time in this section for the second method, which is the elimination method. Because like I mentioned in the beginning of this video, it's kind of harder to get the hang of. So I wanted to make sure we have plenty of time for these examples. So this example, this one's just kind of getting us ready for it. It's not quite, this one's not quite saying, oh, actually, we got one more substitution. I'm sorry. I'm getting ahead of myself. Oops. So this one, we want to still substitute. Let me look at this guy and say, okay, which variable does it look like it's easiest to eliminate? Or not eliminate, sorry, substitute. I'm thinking the y's don't look that good because they have coefficients other than 1. Maybe one of these x's here, I don't know. It's totally up to you. I don't know, maybe the top one. I don't know why that one's calling to me. But it doesn't matter, you could take the bottom one and isolate x in that one, that's fine. So I'm going to take, it was x minus 4 equals negative 2y, and isolate x there. All I would have to do is add the 4 over to the other side, and then I'll have x by itself. This is another one of those times where you have the freedom. You could put negative 2y plus 4, or you could put 4 minus 2y, whichever you're most comfortable with. Okay, now that we have one of the variables isolated, I'm going to take the other equation. Which one have we not looked at yet? The bottom one, huh? X plus 2y equals 6. And I'm going to substitute this value, negative 2y plus 4, in for x. Since the first equation told us that x is equal to that, I should be able to substitute it. So let me see, I'm going to substitute that in parentheses for x, and then we have a 2y, or plus 2y equals 6. Let's see here. So I'm substituting where that x used to be, I'm putting that negative 2y plus 4. And I always do at this point a quick check. Do I only have one variable? If I see both x and y at this point, something's wrong. But no, I only see y's. That's a good sign. That means I've substituted correctly. Alright, now, I don't really need these parentheses. I realize there's nothing really to distribute or anything. So let me just get rid of them. So I have negative 2y plus 4 plus 2y equals 6. I see that there are like terms on the left side, but you notice that they cancel each other out. Negative 2y and 2y is 0. So you're really just left with a 4 on the left and a 6 on the right. This looks strange, right? How am I going to solve for x or y if I don't have any letters left? Okay, so this is a good... I'm glad we came upon this problem, because this is one of those times where... Remember in the last section we said that when you're looking for a solution to a system of equations, your answer is either you're only going to have the lines intersect at one point, which is what we've seen so far. We've only found one ordered pair as a solution. Or they could be the same line in disguise, in which case they have infinitely many solutions, or there could be no solution. So this one is one of those weird cases. So I'm going to point out kind of how do you know which of the weird cases you're in. It's okay, I'm going to say if during the process of substitution, this method that we've been learning, or as a matter of fact, elimination, the next method we learn, what we're about to say goes for both methods. So if during either process, substitution or elimination, the variables disappear, and you are left with, like we have, notice what are we left with here? 4 equals 6. That is a false statement. False statement. There's no solution. And if you remember, that meant that these lines were parallel lines in disguise. But of course, looking at these to begin with, how would I know those are parallel lines? Of course, I'd try all the algebra to see if I'm going to get a solution. This is the only way that algebra is going to tell you there's no solution. So that means this one, there's no solution. But in other situations, there are some where a similar thing happens. So you said as we are solving, the variables disappear, and you're not left with a false statement, you're left with a true statement. So I'm going to say, just in case we come across one of those, if left with a true statement, for example, the one we were left with here is 4 equals 6, but what if it was 4 equals 4, or 6 equals 6? You know, that's actually true. Then that's one of those times where there are infinitely many solutions. Solutions, and that means that these were actually the same line in disguise, that we just didn't realize it until we were kind of thick in the algebra. So we will come across one of those later in this section, but just to keep that in mind, if something happens and all of a sudden your variables disappear, don't think you did something wrong, it's just kind of a strange problem, that's all. Okay. So that's, like we said, that's kind of the end of the substitution problems. Those are good to practice, but I think people get the hang of them a lot quicker than they do this other method. So we're going to try to reserve the rest of the time in this section just for this other method, which is kind of harder to get used to. But this problem here, example 3, is just more of an intro. We're not really using elimination, it's just giving us an idea of what elimination is all about. So notice what the directions say. They say solve the system of equations by adding the equations together. And that's kind of the main idea of elimination is, if you have two equations like we have here, the first one's negative x plus 4y equals 7, the second one's x plus 3y equals 7, you can, if you want to, add the left side and add the right side of the equal sign. So you'll have something equals something where you add like terms on the left. And notice in this one we get kind of lucky because if I try to add these x's, negative x plus x, that's 0. There are no more x's left. If I add the y's though, 4y and 3y make 7y. And if I add the numbers on the right side of the equation, there's a 7 plus a 7, which makes 14. So notice, once we added these two equations, one of the variables was kind of eliminated, I guess. That's why they call this the elimination method. And now we're able to solve for the remaining variable, now that there's only one left. I'll just go ahead and divide both sides by 7. I'll be left with y equals 14 over 2. Or sorry, 14 over 7 is 2. Hello. We found that y equals 2, that means our ordered pair is going to be something comma 2. But I have to figure out what that something is. And what you want to do is take this value, y equals 2, and substitute it into either of the original equations. It doesn't really matter. I think neither one is really better than the other. Sometimes I just choose the one with smaller numbers into either of the originals. It doesn't matter. I'm kind of petty. I'm going to take the bottom one. You should get the same solution no matter which one you choose. Kind of like the bottom one because 3 is smaller than 4. And then also the x is positive, which maybe will make it easier. I don't know. Okay, so we know that y is 2 from the work we did before. I'm going to replace that guy. X plus 3y, but y is 2, so I'll go ahead and replace that. 3 times 2 is 6. And then I'll almost have it. Now I just need to solve all the way for x by subtracting 6 over. Alright, now I know that x is 1. Okay, so that must mean our ordered pair is 1, 2. Alright, so that's the idea of elimination, is to take the two equations, add them together. You're hoping that one of the variables is eliminated, like we had. The negative x and the x combined to make 0. However, you're not usually that lucky. Like, let's see the next example. We'll talk about, oh, oops, look at this. I accidentally put how to solve a system of equations using substitution. It should be elimination. Sorry about that. Elimination. But before we look at the steps, because they're kind of complicated, let's just look at the next example and see why we're going to have a problem. Don't write this down because it's not going to work. If I try to add these two equations, okay, let me try to combine like terms here. 5x and 2x is 7x. So the x's were not eliminated this time. The y's, you have a negative 7y and an 8y. That makes 1y, or just y, equals negative 16 and 26 added together makes 10. And now that I look at what I have, I say, you know what? This isn't helping me at all. I have an equation now with two variables still. There's no way to solve it. So all I've done is combine two equations that I couldn't solve and came up with a third equation that I can't solve. So I didn't really do anything helpful there by adding those. So keep in mind, in the last example, the key was that made it work. It was that the coefficients of x were kind of the same number, right? You had, what was the coefficient of x in the top one? Negative 1. And the coefficient of x in the bottom one was 1. So kind of your goal in these problems is you want either the coefficients of x or the coefficients of y to be the same number, like 1 here, but you want one to have a negative and one to have a positive. Those are the only types of numbers that add up to 0. That's what you want. You want their coefficients to add up to 0. So if that's not going to happen, you have to make it happen. And that's where these kind of steps up here come from. So okay, this is kind of starting from the beginning. It seems like a lot of steps, but once you're doing it by hand, it's a lot less work. It's just kind of, it's a lot of writing to write what you do in math in words, that's all. Okay, first step is, if it's necessary, you want to write both equations in what they call standard form, which just means you have, basically get x and y together, x and y on one side, and then the constant term, whatever c is, on the other side. On the other. Okay, for the most part, that's always the case. Like in this example 4 that we're going to be looking at right now, you have 5x minus 7y. Okay, the x and the y are on the same side. And then the constant term, negative 16, is on the right side. So it's already in that form, and so is the second one. 2x plus 8y equals 26. So usually that step you can skip. That's very rare that you have to do that step. Okay, and then the second step is, now you're going to want to try to decide which variable do you want to eliminate. And I think the best way to do it is it's going to be easiest if you look at the variables x and y. You just say, okay, which of these guys has smaller coefficients? So looking at example 4, I notice the coefficients of x are 5 and 2 respectively. The coefficients of y are negative 7 and 8 respectively. Negative 7 and 8 are larger than 5 and 2. So I think what I'll do is I'm going to try to eliminate x because I think it'll be easier since they have smaller coefficients. So this you don't have to write out, but this will be in my brain. I'm thinking that I will eliminate x. That's kind of my first step, is decide which one to eliminate. Alright, now we're on step 3, where what we want to do, this will become, once you do a lot of these examples, this will all happen in your mind really quickly, and you won't have to write much out. It'll just be all happening really quickly. What we want to do is find the least common multiple of the coefficients of x. So our coefficients are 5 and 2. And by least common multiple, if you want, you can just think of that as least common denominator. So imagine if you had, for example, you had a fraction 1/5 and 1/2. And you wanted to get a common denominator, Like, okay, what would that common denominator be? It would be 10, right? That's the least common denominator. So think of least common multiple as the same as least common denominator. It's just, in this problem, I don't have fractions, so I guess I can't really talk about least common denominator. Okay, so we found the least common multiple. And the rest of basically the next step is us trying to make the coefficients of x. Currently, right now, they're 5 and 2. But what I'd like to see is that I would like to see them both be 10. Although I want one to be negative and one to be positive, like we talked about in the last example. So step 4 will be, you're going to multiply one or both equations by whatever is necessary to transform their current coefficients into the least common multiple, making sure that one is positive and one is negative. So you need them to have opposite signs. So, okay, let's focus on the first equation. The first equation has a 5 as a coefficient of x there. So what I'd like to say is, what would I need to multiply this 5x by to make it into the least common multiple 10? So pretty much what I'm asking is 5 times what is 10? Well, I'd have to multiply that equation by 2, because that would give me the 10x I want. But you're not allowed to just multiply a piece of an equation by 2, or whatever you want. You'd have to multiply the entire equation by 2. But that's fine, it's not a problem. Alright, now that we've done that, I'm going to look at the second equation. The coefficient of x in the second equation is 2, but I would like it to be this least common multiple 10. So I asked myself, okay, 2 times what is 10? Well, 2 times 5 is 10. So, but picture when I multiply the 2 on the top equation, I'm going to get a 10x. And when I multiply the 5 into the bottom equation, I'm going to get a 10x. So that's good because we wanted those numbers to be the same. But keep in mind you want one to be positive and one to be negative. So I have to decide, do I want to multiply the top equation by a negative or the bottom equation by a negative? It doesn't really matter. You just throw the negative on one or the other, just to make sure you're going to get opposite signs. So I think we have it. I'm going to distribute the 2 into the top equation and rewrite it. So if I distribute the 2 times 5x, that's 10x. 2 times negative 7y is negative 14y. 2 times negative 16 is negative 32. That's the top equation transformed, just to make it look a little different. But you know what? The crazy thing is the equation we just wrote, the red equation, it looks completely different than the equation that we started with, the 5x minus 7y equals negative 16. But if you were to graph this line, the original equation that we had, and if you graph the line that results from the equation we just wrote, they're the exact same line. So these are the same equation in disguise. And something similar will happen for the second equation. Let me distribute the negative 5 in there. It's negative 5 times 2x, that's negative 10x. And then you have negative 5 times negative 8, that's negative 40y, equals negative 5 times 26 is negative, I believe, 130. Okay. So now we're left with two equations. They're equivalent to the originals, they just look different. But the whole point of that was so that now I'm finally at the place where I was in the last example, where at the very beginning. We're going to add these two equations together, and it should be that the variable we were focusing on is eliminated. And that's true. Notice 10x and negative 10x make 0 together. And that's good. You should have eliminated that variable. And then when I combine the y's, negative 14y and negative 40y is negative 54y. And the numbers on the other side of the equal sign combine to make negative 162. Okay, that looks good. And then I almost have it solved for y. Let me just rewrite this one more time because that 0 is kind of confusing me. You don't have to write the 0. And now I realize to solve for y, all I have to do is divide by negative 54 on both sides. And that looks like a scary division, but I believe negative 54 goes into negative 162 3 times. Wow, that worked out pretty well, huh? That's a good sign, too, after all that work, if you just get a nice whole number. Okay, so our y value is 3. But now I have to remember that I need to still find the x value. And in this problem, where are we now? We're looking at, we've already done step 5 and 6, because I think it just came natural. Once we combined the equations, we realized that there was only one variable left, so we were ready to solve. And then the next step, step 7, is you're going to substitute into either original equation to find the value of the other variable. And actually, you know what, if you wanted to, you have the freedom. If you want to substitute y equals 3, you can substitute it into either of these transformed equations as well. But I probably wouldn't choose those because they have bigger numbers. You're going to want to choose one of the bottom ones. Or sorry, the original ones. I kind of like the top one better, the 5x minus 7y equals negative 16, because the negative 26 in the bottom one kind of freaks me out. That's a big number. I don't know. It doesn't really matter. Again, if you substitute the y equals 3 into the the bottom equation, that would work as well. It doesn't matter. You're going to get the same answer no matter where you substitute. So I'm taking this equation but replacing the y with 3. And then I should have x pretty soon. That'd be 5x minus 21 is negative 16. And now I'm ready to solve for x by adding the 21 over first. And then I'll have 5x equals, that's 5, right? Hey, this is going to work out nicely. Now when I divide by 5, I find that x is 1. What a nice answer, huh? 1 comma 3. So it's a lot of work. But I guess the alternative, if you think about it, okay, let me see. Think about what we would have to do if we didn't use the elimination method on this one. It kind of looks muddled right now, but I'm just going to rewrite just to talk about it. The original system was looking like 5x minus 7y equals negative 16. 2x plus 8y is 26. What if we try to use substitution on this? I think that would be very bad. Because if you use substitution, you'd have to isolate either x or y in one of the equations. That's going to be ugly. Yeah, I think this one would not be fun for substitution. So even though elimination, it seemed kind of complicated, this one would not have been pretty for substitution either. So don't worry. This is the best way to do this problem, I think. All right, that's kind of a whirlwind. It takes a lot of practice, so let's see a few more. Because these are, kind of difficult. And feel free to keep looking back at the directions if you don't remember what to do exactly. So, okay, example 5 now. We have two equations, and of course they gave us weird variables, s and t. Why do they do that? I don't know. But what we're supposed to do is see, all right, do I want to eliminate s or t? So I look at the coefficients of s, and I look at the coefficients of t, and ask myself, which one has smaller coefficients? Well, to me, as soon as I see this 91 on t, I say, oh no, I don't want to work with that guy. So I think on this one, I will eliminate s. It's going to be a lot nicer, a lot easier. So as it says, what I have to do is think about what's the least common multiple of the coefficients of s. So what are the coefficients of s? 2 and negative 14. Okay. So that if you kind of don't feel comfortable with least common multiple, what you can think about is, what if those were fractions? 1/2 and 1 over negative 14. What you're really looking for is what's their kind of like least common denominator. Well, if you have a denominator of 2 and a denominator of 14, the least common multiple would be 14, wouldn't it? Yeah, because all you'd have to do is multiply the top or the first one by 7. Yeah, okay. So that just gave me the right idea. Now I know that I want both coefficients to be the LCM, the number 14. So now I'm gonna look at the top equation first. I'm gonna ask myself, what would I have to multiply 2s by to get 14s? Or in other words, 2 times what is 14? Well, that'd be 7. So I better multiply the top equation by 7. Okay, so we got the top equation down. And then I look at the bottom one and I say, negative 14s times what is 14s? Well, it's already a 14, so I don't think I really need to multiply by anything. And also, notice the other thing that we wanted was, you want the coefficients of s, or whatever variable you're eliminating, to be the same number but with opposite sign. And you know what? I don't even have to touch the second one, because that's going to be perfect. Once I distribute the 7 into the top one, I'll have a 14s, and the bottom one's a negative 14s. It's already perfect the way it is. So there are times where you kind of get lucky and only one of the equations has to be multiplied by something and the other one does not. So I'm just going to multiply the top one by 7. That'll give me 7 times 2s is 14s. 7 times negative 13t is negative 91t. And then 7 times 120 is, let's see, 840. That's looking a little familiar, right? That's kind of scaring me. So that was the top one. And then the bottom one, we already said it's perfect as is. There's no need to multiply it by anything. I'm just going to rewrite it. Negative 14s, this is interesting, plus 91t, okay, equals negative 840. You notice these numbers are all the same. I know something funny's going on here. But whatever. I'll just pretend like nothing's going on. And the next step was you're supposed to add these equations. And the whole point of doing what I've done so far is so that the s's cancel. That was my goal. But now I notice that once I cancel the s's, the t's cancel as well. Because negative 91t and 91t is 0. There's nothing left on the left side. On the right side, you have 840 and negative 840. They add up to 0 as well. So all that work, this is one of those weird situations. Remember we said above, where was it? A couple examples back. It was here. Okay, we said if the variables disappear, like just that exactly just happened. X and Y, or sorry, S and T just disappeared. But this time we're in the situation in red writing here. If you're left with a true statement, that's what we have. 0 equals 0. That means there are infinitely many solutions. Aha! So we must be in that situation where these were the same line in disguise and we just didn't know it. Okay, so I'm going to write that down. There are infinite solutions. That means these were the same line in disguise. But if you remember from the previous section, we said if you have the same line in disguise, the way to write your solution, and they call it set builder notation. Builder notation. What they want us to write is all the points. That's really what this means. I want all the points such that, and then all you have to do is grab one of the original equations. It doesn't matter because, like we said, they're the same line, so those are actually the same equation in disguise. It doesn't matter, I'll just grab the top one, sure. And you know what, I'm realizing there's a problem here. What are our solutions? Are they going to look like x comma y in this one? No, our variables are s and t. Ah, I should have put st, I'm sorry. So all the points s comma t, such that yada yada yada. This is the way you're technically supposed to write the answers to these problems where there are infinitely many solutions. But really, just remember that means I want all the points that are on the line, because they share every point in common that's on the line. Okay, so those are kind of strange situations. So keep that in mind. Those are kind of tricky. Alright, we got 2 more examples here. I'm sorry, it's such a long section, but the more of these you practice or you watch, the more it'll make sense. Well, the next example, example 6, this does not look pretty. I have a bunch of fractions here, which I'm not too excited about. 1/3 x, 1/5 y, 1/6 x. But if you remember, whenever you have multiple fractions in an equation, you don't have to keep the fractions. What I'm going to do is multiply either equation, multiply by the least common denominator in that equation to get rid of fractions. I think I'll do that first before I even try to solve this with elimination. I'm just going to try to get rid of fractions. But I'm going to treat these equations as independent of each other. So in the top equation, I look at the denominators. You have a 3 and a 5. The least common denominator there would be 15. I'm going to go ahead and multiply that in there. And then I'll do this, or something similar to the second one, but I'm just going to write that out. Let's see. The top equation will become 15 times, okay, we had 1/3 x. I'm going to see how that looks, plus, I'm also distributing the 15 onto the 1/5 y. Put that right next to it so I don't mess it up. And then the 7 on the other side is also multiplied by 15. Alright, I'm going to simplify that, but leave room for the second equation. Let me see. If I put that 15 over 1, the 3 can go into the 15 5 times, and you're just left with 5x there. If I do that for the second term, put the 15 over 1, the 5 can go into 15 3 times, and you'll be left with plus 3y. That looks a lot nicer. And then on the other side of the equation, you have 7 times 15, that's 105. Oh, I'd much rather deal with that than the equation that we started with. Thank God. Alright, now let's try to do the same thing for the second equation. Let me look at that guy. His denominators are 6 and 5. The common denominator between 6 and 5 is 30. Let me multiply that into all 3 terms on that equation. It'll be 13 times the 1/6x minus, and then 30 times the 2/5 y equals 30 times the -4 on the other side. So it was 1/6 x minus 30 times the 2/5 y, and then 30 times -4. And we'll see how that simplifies. I'm going to put this 30 over 1 here in front of the x. 6 can go into 35 times? Is that right? Wait, really? Wow. That becomes a 5x. That's kind of nice. And here, I'm going to put this 30 over 1 and reduce. 5 can go into 36 times. 6 times 2 is what's left. 6 times 2 is 12. So that'll still be a 12y. And don't forget it's a negative because there was already a negative to begin with between the two. Now on the other side of the equation, it's 30 times negative 4, that's negative 120. Alright, this looks a lot nicer to solve. I'd much rather solve this problem here. So now I'm going to look at now I want to start eliminating. That was all just trying to make this look good so I can finally do the elimination method. So looking at the coefficients of x and the coefficients of y, I kind of like the coefficients of x, because remember the goal is to get either the coefficients of x to be the same number, opposite signs, or the coefficients of y to be the same number, opposite signs. I'm looking at the x terms, they're already the same number, all I need is for them to be opposite signs. So really all I would need to do is multiply either the top one or the bottom one by negative 1 maybe, because I just want one of them to be positive and one to be negative. And yeah, it didn't matter which one I multiplied by negative 1, I just kind of chose the second one, I don't know why. So I'm just going to keep the top one the same, it's perfect as is. It already looks good, but the bottom one, I'm multiplying every term by negative 1. But what that really does is it changes everybody's sign. The 5x will become negative 5x, the negative 12y will become positive 12y, and the negative 120 will become positive 120. Alright, we've done it. That was the whole goal, is to get their coefficients to be the same number, opposite signs. Now we're going to add them together. And of course the 5x and the negative 5x, that's 0, those disappear. 3y and 12y is 15y. On the other side I have 105 and 120, that's 225. Okay. And then we can solve for y pretty quickly by dividing both sides by 15. Let's see what we get there. See, I don't think that goes in evenly, does it? Oh, maybe it does. How many times does 15 go into 225? I have no idea. 15 go into 22 once. With 7 left over. 15 goes into 75 5 times. Oh, so it's 15. Huh. I did not realize that. So that y equals 15. That's the guy. But remember, these problems, you should always have an x and a y value. So I have half of the solution. The other half I don't have. But once you find one variable, it's a lot nicer. It's not too much work left. So now I can go back and look, which equation do I want to substitute y equals 15 into? You know what I would do is probably not use one of the originals. Those are not nice. They have ugly fractions. I'm probably going to try to grab the ones that I transform them into. Either this one here in the blue box that I just made, 5x plus 3y equals 105. That's pretty good looking. Plus 3y, 105. Or the second one's good too. The 5x minus 12y is 120. But I think that's a good one. The 5x plus 3y is 105. I'd much rather deal with that than those fractions that we started with. So I'm replacing the y with 15 since we found that y is 15. Let's see, y is 15. Let's put that where y was in that equation. And then what would we have left there? 5x plus, that's 45, I believe. 3 times 15 equals 105. And we'll start solving for x and we'll be on our way to being done. Move the 45 over so that 5x is, let's see, 105. Oops, sorry. 105 minus 45 is, don't tell me, 60. And the last step will be divide by 5. So x must be, what is that, 12? Yeah, 12. All right. There we go. So I got our solution. 12 comma 15. That'll be the guy. All right. That was kind of painful. I think it was only because it started off with fractions. That was why it was so bad. Because remember, all we would have to do is the work from this stage on if we didn't start with fractions. Just the fact that we started with fractions made it kind of difficult. So that problem is probably a worst case scenario. You have fractions, so it ends up being pretty bad. Okay, and the last example we have here is kind of similar. You're starting with decimals, which I really don't like decimals. I think I like decimals even less than I like fractions for some reason. But remember, like in the last example, we multiplied each entire equation by the least common denominator to get rid of the fractions. But remember, when you have decimals, what you want to multiply by is 10, 100, 1,000, whatever you need. 10, 100. It kind of depends how many times would I need to move the decimals over to make them whole numbers. But if you look at all these decimals, 0.3, 0.2, 0.3, 0.5, 0.4, all of them only have one digit beyond the decimal. So I think I'm okay to multiply the whole first equation by 10, and the whole second equation by 10. That would move everybody's decimal over to the right once, and that's all I would really need. So let me try to go ahead and do that and rewrite these guys. So let's see, the top equation would become, if I multiply 10 times 0.3x, that would be 3x. 10 times 0.2y would just be 2y. 10 times 0.3 would be 3. Oh, that's a lot better. Let's see what the second one would look like. 10 times 0.5 would be 5x. 10 times 0.4y would be 4y. And 10 times 0.4 is 4. Oh my gosh, that's way better. That's a much better system. I'd much rather solve that one. So let me see. Looking at those, now I have to decide which one to eliminate. Do I want to eliminate x or y? Let me see. Well, the coefficients of x are 3 and 5. The coefficients of y are 2 and 4. 2 and 4 to me are smaller numbers, right? So I think I'm going to choose y to eliminate. But what I have to do now is think, okay, what's the least common multiple of the coefficients of y? The coefficients of y are 2 and 4. I imagine if I had fractions with denominators 2 and 4, their common denominator would be 4. So that must be what I want. I want to transform both of those equations so that they have a denominator of 4. So let me see, I'm going to rewrite the top one here. And then just think, what would I have to multiply that equation by to make this a 4 here? I'm going to say, I guess 2, huh? 2 times 2y would be 4y. But in the second equation, what do we have? 5x plus 4y is 4. I'm thinking, okay, that actually the coefficient of y is already 4, so that's perfect. However, I remember that you want the coefficients of y, or whatever variable you're eliminating, you want them to not only be the same number, but you want them to be opposite signs. So I need one of these to be a negative 4. And I feel like, I could multiply the bottom equation by a negative, but I feel like I'm already multiplying the top equation by 2. I might as well multiply it by a negative, right? Make it a negative 2, and that takes care of your problems. And I won't even have to touch the bottom equation. So it's totally up to you. You could have multiplied just the top one by 2, and then the bottom one multiply it by negative 1. But I think just multiplying the top one by negative 2 would get rid of all your problems, and I don't have to do anything to the second one, because it's kind of perfect as is. Alright, let me see. I'm just going to take the top equation and rewrite it here, multiplying the negative 2 in. Negative 2 times 3x would be negative 6x. Negative 2 times 2y would be negative 4y. Negative 2 times 3 would be negative 6. So that top equation transformed into the one we just wrote. The bottom equation, we already said that we don't need to do anything to it. It's already perfect. It has the coefficient of y we want. And now I'm going to add these guys together and see what I get. So I've got here a negative 6x and a 5x make negative x. Or you could write negative 1x if you want. The negative 4y and the 4y cancel, that's 0. So no need to even write anything. On the other side, negative 6 and 4 make negative 2. Alright, now we almost have x by itself now. It's actually easy to solve for x. I just need to get rid of the negative that's in the front of it, and all I have to do that is divide by negative 1. And then I'll know the value of x. X is negative 2 divided by negative 1 is 2. Okay, there we have it. We know x, so I know my answer is going to look like 2 comma something. I just don't know y, and no pun intended, y, the variable. So now I need to substitute x equals 2 into either of the original equations or one of the equations I transformed them into. I think I'd rather not deal with either of the originals. I'm going to try to look at either this blue one that we wrote just below them or the red one we wrote below them. Well, the blue one has slightly smaller numbers. That's how petty I am. I'm going to grab onto that one. That one looks a little bit nicer. But now I'm replacing the x with 2. And see how that looks. What if the x is 2? Okay. Then it would be 3 times 2, that's 6, plus 2y equals 3. And if I want to solve for y, I'm going to subtract 6 over to the other side. And that way I'm left with 2y equals negative 3. And I'll have y by itself if I just divide both sides by 2. So y must be, and 2 doesn't go in evenly, so I'll just leave it as a fraction. Negative 3 halves. And don't feel like just because you got a fraction as an answer, or as one of your components, you did something wrong. You probably did it right, so don't worry. There's probably 10% of the time you're going to get a fraction answer. But I think that's the end of that section. Thanks for listening. The next section will be lots of fun. We'll do applications of these. But usually the equations are really nice. They're not as bad as these. So thanks for listening. Have a good day.